This presentation is looking at electrochemistry from the aspect of EMF, free energy, that's G, and equilibrium, so variables like K or Q. So as the title alluded to it, we can connect the cell potential, the EMF, and Gibbs free energy, which is G. So just to help you out, EMF, we're going to call that E, and Gibbs free energy is delta G, just to help you remember what we're dealing with. And there's an equation for that, of course there is, and it is delta G equals negative NFE. So delta G we know is a Gibbs free energy, and E is our cell potential, our E. So that only leaves us two new variables, and we've dealt with moles before, but in this case, N is going to be the number of electrons transferred. So when you balance those chemical equations, you have electrons being lost and electrons being gained, and they should cancel out. So the number of electrons being transferred is the value that you're going to plug into your N value. F stands for Faraday's constant, which is 96,500 coulombs per mole. It also has another unit called joules over volt per mole. So you are going to need to memorize this. This number is not going to change. And the only real changes are the cell potential, the free energy, and the number of electrons transferred. Keep in mind there's a negative sign in there. So delta G equals negative NFE. Positive E and a negative delta G both indicate a spontaneous reaction. Remember all along in the thermochemistry chapter we just got done doing that our negative delta G indicated spontaneous. So if you have a negative delta G in this problem and you have a positive E, it's still telling you that the reaction will go on its own. You can also then take this into standard conditions. And by doing standard conditions, you get that zero in the air. So delta G zero equals negative NFE zero. And so you're able to then calculate spontaneity with another, looking at a different factor. So to add another complication, we just did our delta G equals negative NFE values. We have a new equation called the Nernst equation, and this Nernst equation is how we're going to link in equilibrium. And in equilibrium, we had a constant of K, and that was the reaction constant where we took the products over the reactants. And then we also had Q, and that was for the initial conditions. So I'm going to just put an I there to help us remember that that was at initial conditions. So when we are looking at the concentration in a particular cell, and we're going to be looking at those values and deciding how that affects the spontaneity and the free energy. What we're going to do is we're going to take our delta G equals delta G zero plus RT natural log of Q that we would have used in our thermochemistry equations, and we're going to substitute in the E values that we just connected to the problem. And when you do that, you do a little equation derivation. We have that N and F that needs to translate as well. So when you do that, you end up with an equation that looks like this. E equals E0 minus RT over NF, natural log of Q. So at 298, that gets rid of our temperature. F is a value that is calculatable, and R, we know that's a number as well. So we can then do a little bit of additional derivation, and you get to be able to use this equation is the one that you're going to find much more useful. So we'll go ahead and star this one so that you remember this one. And E equals E0 minus 0.0592 volts V over N, that's your number of electrons transferred, times the log of Q. And remember, Q is going to be found by taking the products concentration over the reactants concentration. And remember, if you have a coefficient, you raise it to the power of the coefficient. So if there was two H2s, you have to square the H2 concentration. Lots of things to remember here. Not terribly challenging, but you just need to dig back into your recollection of equilibrium in order to be able to use this equation correctly. So when you're dealing with Q versus K, Q is the initial conditions and K is at equilibrium. So we can then alter this equation and we're going to say, okay, delta G is 0 at equilibrium. So E is 0 also. If you look at the delta G equals negative NFE, the delta G would be 0. And so that would then lead it to that product would also be 0. So you were able to take the Nernst equation and modify it. And if you're looking at equilibrium, you would then use this equation, log of K equals N for the number of electrons times E0 for the cell over 0.0592 to use to help you find E cells, E values, and Q or K. Remember, K is at equilibrium and Q is at the initial starting concentrations.